I've spent a good portion of my life in acoustic labs, and most of you probably have not had that experience. And I'm happy to show you some of the many things that we do. And so we're going to be talking about acoustic material testing, and mainly I'm going to be showing you what we do when we're talking about when we're testing materials. And when we say testing materials, I mean it could be a material, it could be a composite, it could be a full product. When we're developing, we're constantly making tests, and then maybe making some modeling adjustments, because and then going back and making more tests, and so anyway, I'm going to go through that, and I'm going to show you, I guess, 3 different labs that that I frequent, and then the second part will be about diffusion confusion, just because this is so on my mind right now. It seems that like this last year or so, I'm seeing all kinds of misuse of diffusers, and so I want to cover that a little bit in hopes that you guys will help spread the word regarding the the diffusion confusion that is out there. Okay, so whether noise control or sound quality, there is always a prescription. So when we're talking about treating studio, a critical listening space, we have to gather data. In order to make it perform the way we want it to, we have to know how is it performing now. And so we can then know the acoustic characteristics of the existing conditions, and then model with data that we've got from acoustic labs regarding products and how they perform, so that then we can ultimately get to the goal, our target, what we want the room to behave like. So we got to collect the existing data. We've got to know we've got to determine with the client what the desired goals are. And there's always going to be constraints. We need to understand them. And my job as an acoustical engineer is to help the client understand, every room is a compromise. There's no such thing as a perfect room. We are always going to be running into constraints or limitations, and they might be budgetary, they might be time, they might be physical space or load. It could be decor. There's a lot of constraints that come into the equation. Then we're going to computer model. I'm going to help the client understand the pros and cons of different solutions, so that then recommendations can be made by the client, so that he can make an informed decision. So this is how we get from the existing conditions to the goal, and it's all about organizing sound from chaos. The goal is a neutral environment, right? We want to be able to mix in a facility that will translate well to another facility. So in other words, the environments must be neutral, or as neutral as we can possibly make them, so that we aren't, when we mix, influenced by the room conditions and affecting our outcome. And then it goes to another facility with a different set of conditions, and it gets all screwed up. So the idea is we're all on a level playing ground, a neutral environment, a foundation that is proper to do our work. So the data from the environment and the products are required. So this is, I'm from California. I was born and raised in Southern California, and then I had a high-end audio store in Northern California, and that's where. And I was doing acoustical work. I'm a drummer, recording engineer, and I've done all this since I was really little. And so it's all about the music to me, and that's my passion. I want to make the music as emotional, as accurate as possible. And so early on, I learned that acoustics is key. You can have state-of-the-art equipment, and if the environment isn't right, it will never achieve its potential. And on the other hand, you could have mid-fi, set it up in a controlled environment, and it can sound awesome. So anyway, I was working for MIT at the time, and Owens Corning, who's out in Ohio, that's where I'm at now, is in Ohio, in central Ohio. And this lab is 10 minutes from my home right now. And it doesn't look like much in front, but it's on the top of a mountain, rather a hill, and it goes back quite a bit and then down deep into the ground. And I'll show you some examples of what I'm talking about. So, and I'm just going to show you some examples of these different facilities and some of the work that I did there. So one of the first things that I did, they had some product, some acoustical product, and didn't really know how to apply it. And that's why they hired me. And so first thing I wanted to do was to really characterize we knew how the product performed in the lab, but how do we apply it to the real world? And so I built two rooms. These are, I call them AB rooms because one is after treatment and one is before. I built them so that noise control wasn't going to play into it, and room modes were distributed pretty evenly. Other than that, they're typical. The construction's typical, the furnishings are typical, and they're exactly set up identically the same. And let's see, I think I've got a picture. Yeah, so here's an interior of one of them. So you can see there's sofas. This was in 1998, 99. Home theaters, when home theater was beginning to really explode. And so we wanted to address that market with what they call the acoustics, ARS, acoustic room system, which was a couple of different panels that did different things. And so here I am mapping out the room. First, have to characterize the room. So you can see those little pieces of tape all over the floor and all over the sofas. So I just grid and was taking measurements at every one of those spots in both rooms, with and without the treatment. And I set them up precisely with you can see I'm using I'm aiming these things with lasers. So they're physically and as well as electronically calibrated precisely. This, I had just a decent system. Those are those speakers there. We had a 5.2 setup in there, same speaker all the way around, and a couple of subwoofers. And what was interesting about this is that we had at Owens Corning, there were about 600 scientists at this facility at the time from all over the world. So a good conglomerate of people. We also had our own medical facility there 24/7. And inside there, we even had our own audiology room. And every year, everyone had to have a physical, and that included hearing. So I noticed every once in a while, you have to do these little dog and pony shows, we called them, for VIPs. When some VIP would, or several, they would come in and you would have to explain the research and development that you were doing at the time. And I was playing a little sample of the before and after treated rooms of a movie called Das Boot. I don't know if any of you recall that, or I mean, that came out quite a while ago. Great movie. And there's a 7-minute clip that I would play. And anyway, I noticed after that several of these VIPs after the treated room, and these guys, they don't know anything about audio. They don't really care, but they would say, I would love to have this in my home, And so it got me thinking, okay, it's not just me who understands and appreciates audio, it's anybody. The average Joe with no knowledge, no care, is being impressed by this. So I thought, hey, we've got a staff here that can help me out. Let's do biofeedback tests on people. And so I put together a window of hearing that needs to be met and asked for volunteers. And I got about a dozen volunteers, and we hooked them up with we were checking perspiration, respiration, blood pressure, heart rate, all those vitals, all those biofeedback um, indicators. And we would have them cool down, take their measurements, play in one or the other. We would alternate, let them cool, and then go into the other room. And with all of those, with the exception of one guy who must have had something on his mind, because he was just like flatline the whole time. Everyone else in the acoustically treated room, their blood pressure, their heart rate, all that. So you could even see, okay, this person was affected by when the sub's trying to sink, to dive down below where it was designed to withstand the pressure, to avoid from they were evading ships up above dropping what do you call them, bombs into the water. And so at first it's the hull creaking, and then rivets are flying, and then a guy gets hit and there's blood, and then there's water coming in. You can see these different events and how it affected different people. Anyway, to me, this was so cool. And one of my favorite parts of my career is that it proved that acoustics controls your emotion, and having quality acoustics is unconsciously made is appreciated unconsciously by anyone. So anyway, that was a highlight. So in this room, this is further back and way down in the earth. We built a room, really kind of we built a house inside of the lab. So this is actually a 3-story house, and it's 2 of them. So there's a basement, there's a first story, and there's a second story. And so we were able to do all kinds of, noise rated systems, doors, seals. We were able to check out all kinds of things in real world conditions, not just the lab. So that's pretty impressive. That is gone now. Recently, just this last year, this year, they've removed the house, and now they're building a giant means of doing impact on floors and or ceiling partitions. So anyway, it's pretty cool. Very cool, as a matter of fact. This is another. This is we did jury studies here too. So this is 3 rooms and a listening room. So we had a listening room and 3 rooms around it, and we would have different systems for noise control and or sound quality, and we would have people come in and evaluate these. And so this is also pretty enlightening when you can begin to correlate your test data with perception, and that's tough. That's difficult to do. It takes a team to do this. I just designed the system and the rooms and so forth. This is the control center for those rooms, for those 3 rooms. And
Norman, how long do you think this photograph would be from? How old would this photograph be?
Well, let's see. This would have been probably around 2000.
Pretty
Yeah. So
old. Would you like to? Would you like to? Yeah, but you look so really cool in that really tech savvy room. And would you like to share like what kind of oralization rooms were used to be back then compared to today? So everyone kind of gets an idea like what really oralization rooms are for, and maybe what they were for in back in the day. Is there any difference so far?
well, okay. So this particular project was for particular products that Owens Corning made. So they were designed specifically for wall systems. We had at the time acoustic wall framing. It was a resilient. It doesn't exist anymore. It's too cost prohibitive. Um, so it was about that kind of thing, and so we were collecting. Again, we know how it performs in the lab, but when it's out in the field, it can be something different. And beyond that, how perceptual is it? How meaningful is it? And so we needed to collect data on that as well. And so that's what this jury study, I call it, was all about. This is one of the reverberation chambers. So Owens Corning's got just all kinds of. I mean, it's one of the best labs in the world. And anyway, this is when you've got a reverberation chamber, it's always one next to another so that you can do. Well, I not always, but typically, so that you can do transmission loss as well. But this is the main reverberation chamber, and here here you can see right hanging down is a big vane. That vane it goes around about 6 revolutions per minute. And what that does is in a reverberation chamber, you see that there are diffusers. So now this is a it's got to be quiet. So it's a room within a room within a room. It's completely isolated. So the it's completely isolated mechanically from the earth, from the rest of the building, and so forth. And it has concrete everywhere that is then also painted. So it's super reflective, very thick concrete. Um, the idea is to make the sound continuously go back and forth so that from a sound pressure point of view, when you're away from the boundaries, um, frequency response, even phase is the same. You have down there some material being tested. Typically, and we'll talk about another reverberation chamber that is not typical. Typically, you have 72 square feet of material, whatever that is, if you're doing sound absorption coefficients, for example, that need to be placed in the middle of the room, and then you blast the sound in the chamber and record how quickly it dissipates by frequency. So it's time over frequency. You end up with a curve. And I know so often in acoustics, we are dealing, and this is an important point. You'll receive from a manufacturer a number, and it might be TL, it might be STC, it might be NRC, at all kinds of places where they'll put a single number. A single number doesn't tell you anything. It's almost completely useless. You have to see the curve. You have to know, how is this material performing, either from a sound transmission loss or a noise absorption. How is it performing across the different frequencies? That way, when you find that, okay, I've got quite a bit of reverberation in the mid range here, what's a product that will address that? Or it's hanging down here in the low. Shoot, most of these products don't do that. You have to have the whole story. So yeah, reverberation chamber. Now let me go back. You see that opening on the other side, it's all closed off there. Well, here I am on the other side in the other reverberation chamber. doing a transmission loss test. This is a product that we make. It's a constrained layer compound. And so in this side of the reverberation chamber, we have loudspeakers that will transmit sound through or not the dividing partition, whatever that is. And then you have microphones on, actually you have microphones on both sides, but then on the other side, it will record what gets through, what sound energy gets through, again, across the bandwidth. Now, these chambers, are not particularly small, but they're good down to about 40 hertz. I'll show you a chamber that's good down to 25. So now here again, still at Owens Corning, this is they had at the time, it was one of the largest anechoic chambers in North America. This is a fully anechoic chamber in this condition here, but it can be made semi-anechoic as well. Those wedges, those are 4 feet deep or 4 feet thick. And I'm on a steel grid. So it's kind of like a trampoline. When you walk around, it's very springy. And here I'm doing a test. I'm just checking out. This is an existing product that they made. It's a diffuser, not a good one. And anyway, still though, needed to characterize it. So I'm doing propagation, essentially, looking at scattering every 5 degrees. So this is on a pole, and I'm just swinging it around. Interesting. In anechoic, again, I was talking about having VIPs come in. So there were a couple of times where I would have a VIP come in to a fully anechoic chamber, and they would get nauseous, very uncomfortable. And so, going in ahead of time, I'd ask, because you don't want them throwing up on on those wedges down there. And it did happen a couple of times. So what was happening? It's just a psychoacoustic response. So upon entering an anechoic chamber, you don't have any reflections coming back at you. And it's a strange phenomenon because you've never experienced that before. So what's happening is your brain's getting very confused. It sees boundaries, but it doesn't hear boundaries. And so it just gets confused, and it results in some people feeling sick. Now it is not something that, we have all experienced anechoic experiences. That is, for example, out in a open field, we don't have any returns coming back to us, or with headphones, it's anechoic too, and we don't get sick. But we've experienced that. Heck, I've spent, I don't know how much, again, a good percentage of my life in these chambers, and I don't get sick, but it's because I've experienced it. Let's see, another shot. So another test on this this diffuser. This was it was resonating, and so I was trying to find a material that we could back it with to dampen damp the material. And so they had, this was big time back then. It still is. Laser vibrometers are still a big deal. They're expensive. But back then, this is one of the few places that had a laser vibrometer. And this is just, look, I'm actually, checking and making sure it's hitting all the points. Airflow resistivity are, you've got fabric that goes over acoustic materials. It's got to be, you've got to know how it's performing, because you're talking, especially when you're talking about a stretch fabric system, that's a lot of material that has to be a part of the equation when you're doing the modeling for the room. So you have to know its properties as well. Even if it's something that's very porous, it's going to have quite a bit of absorption properties that you've got to account for. This is back then we called it acoustic holography, and here we were trying to work on an enclosure for a manufacturer to control. If we didn't have an enclosure, then the noise would just go through the entire cavity and spread throughout, on the other side of the wall to the other room and whatever. So anyway, here we've got a whole bunch of calibrated microphones, and we're looking at essentially mapping from a two-dimensional plane a sound intensity holograph of how well it's performing. So we're trying to find out, where is it leaking? Where's some of the sound being compromised from? Early stuff. Now here's later. This is after I was no longer working at Owens Corning, but working at Owens Corning for another project. And so this is what they call now. This is early though, acoustic photography. And so here you had, I was working on a diaphragmatic absorber for low frequency absorption. And so putting it on sheathing, and then you had a wand that you would go across in real time. And you can see in the computer down there, the image, again, showing intensity. Well, now they have, fancier acoustic. You don't have you're not manually doing it. It's on an arm and going around. And anyway, they have much fancier ones these days. So now another lab. This is NWAA, which is in the state of Washington. This is a fantastic, really unique lab. And one thing that's cool about it is that it was a nuclear power plant that never got commissioned. They got some of the water in there, but it never got fired up because then, I don't know if you were aware of, there's a 3 Mile Island nuclear disaster. And so that shut it down. So it never was commissioned. It never was turned on. But the lab, the facility is totally set up for acoustics. So the reverberation chambers are where it's shown there. You have no idea how big this picture is in reality, but I'll try and give you a little idea. So this has the 2 largest reverberation chambers in the world, and these, with no deficiencies, are accurate down to 25 hertz. And you can measure down below that. So I use this lab a lot because it's the only lab that will give me credible data in those low frequency ranges. Not only the 2 largest reverberation chambers in the world, but the 2 quietest reverberation chambers in the world. You can see this is a loudspeaker system. It's only part of it. You can see up above a bunch of tweeters. Again, there's diffusers and so forth in the facility. Another one of the speakers you can see below and as well as above, and the diffusers. So here, people may not think about the fact that when you're talking about an acoustical product, this is a diffuser. These are a barrel type of diffuser. Well, you introduce a bunch of those, and you're going to have some absorption too. So besides diffusion, we need to check what are the absorption coefficients so that the acoustical engineer will be able to, again, implement that into his modeling so that the result is good. Now this is, again, at NWAA, totally unique. This facility, that ceiling there is 80 feet tall. And the building itself will house, is it 4 or is it 6 football fields? It's massive. Those wedges there are 5 feet tall. What we're doing here is testing one of our diffusers. So above my head is a turnstile, and on that arc are 19 calibrated microphones. And then a speaker right in the very end of it up on top. So you blast down onto the speaker and then record as you're turning in 1 degree increments the scattering result. And so then you end up with a a balloon plot, what looks like a three-dimensional balloon plot. In fact, in the computer, it is three-dimensional. That facility, and this will test distribution, dispersion of loudspeakers, and obviously diffusers too, is the best. There's nothing like that in the world. Excellent facility. Another shot, another day. Shows better the turnstile there. And then also, these products have to be fire rated. If they're going to go into a commercial or residential facility, you've got to know, and in fact, there are codes, especially in the States, that, it is a requirement. This has to be whatever, Class A rated, or the California corner burn test. And so anyway, this is a product that I was working. This is our constrained layer damping material. So we had to make sure, though it's sandwiched in between sheathing, that it would pass what is called here a Class A fire rating. And anyway, so this is a tunnel, and on down here is where the flame starts, and over time you see how long it takes for the flame to spread and the smoke to spread too. You record both. This is now at Kinetics Noise Control, where I was studying floor impacts, and so this is a rig that I designed to do such a thing. And so we've got accelerometers all around it, and are recording various impacts, and then materials between the flooring and the impact. Another shot of it with a particular flooring system on it. So there you can see a 16-pound shot that I just drop with a rope. So it's consistent. Again, part of standard tests is they've got to be repeatable, and they've got to be consistent. Another shot with a different type of mat down below, and again, accelerometers all around, on top, above, so that we can get all 6 degrees. Resonance. Products like these acoustical panels, they have resonance. So that means they're going to be amplifying particular frequencies. Again, we've got to know what they are and or how to control them. So this is also an impact test. This particular one is a small little hammer in my hand there. That's a small hammer. They make even smaller hammers, and they make big hammers too. You can use this to find the resonance of a building or a bridge. Compression, yeah, it's just this is the product that we make. Actually, it's unique to my company. It's the equipment vibration protector, and so we make it in different sizes and different densities. In fact, I've got a couple. These are the typical ones. We make different sizes and different densities. We also make different shapes, and we make custom ones all the time. This is different layers of fiberglass. And so,
do you want to turn off the screen sharing so that everybody could see that better, what you were showing?
Yeah.
Actually, we can only see your screen, your video as a very small icon on the left. If you turn off the screen sharing, that would be enlarged up.
Yeah. So there is a video on our website that I do a little demonstration with a music box. So I'll tell you about it. So it's layers of fiberglass, different layers of, the more layers, the denser the material, the heavier the load can be. But the key is, I don't want to have any resonances in the audible bandwidth. So I want to make sure that the natural loaded resonant frequency is at least an octave below the lowest frequency I'm interested in, which would be what, 20 hertz? So I want it to be at least 10 hertz. When we designed this, and all the products that we make, regardless of the size or the load, They're going to be designed to have a natural resonant frequency of 3.4 hertz, and they become effective right at 5 hertz on up. And conservatively, they'll mitigate 90% of the energy from 5 hertz on up. And to give you an idea of to me, this is this acoustical product. It's like the least expensive product we sell. It is the most effective product that we sell from so many points of view. You put these under sensitive electronics, but primarily I recommend putting them under loudspeakers and or subwoofers. These should be, if you've got any monitors, these should be under them so that the vibrations aren't transmitted to the structure. There's several reasons why this is a big plus. One, super easy to do. Two, it's very
I'm really sorry to interrupt.
Yeah.
These things just get me very curious. Like we're always using a lot of decouplers in all kinds of studio projects. So I didn't know that you manufacture this, and that's really wrong on my part that I didn't do much research about your company. But I'm really curious about these products. Like would you like to explain like what is basically the working fundamental behind these? How do you handle the rocking modes? Plus, what are the reflection factors that are needed for these products to be activated? Plus, do you ship internationally?
Oh gosh, yeah, we sell these things all over the world.
Just be sure to send me a link. I'll post it in the group. I'm sure many people would be interested.
Well, that's why I wasn't planning on going into this heavy, but because like I say, this is the biggest bang for the buck regarding. So let's explain why. Isolation of your loudspeakers. So that's your source of vibration. And typically they're just resting on the structure and everything's hard fastened. So if it's resting on the, let's say on the floor or on a shelf that's then resting on the floor, then it's getting to the floor and it's getting to the walls and the ceiling and the furnishings. And this is why, for example, a subwoofer, you can hear the low frequencies in another part of the building because it's in the structure. If you, excuse me, if you isolate that subwoofer, that won't be the case. It hits every sound quality attribute. I don't know of any acoustical product that hits all the sound quality attributes, affects all the sound quality attributes, nor do I know one that is also noise control. So again, put it under the subwoofer, you don't hear it in an adjacent space. So it's a fantastic product. So what is the benefit of isolating your sound source? So when you have a speaker, a sound source coupled to the structure, so in other words, your monitor or your subwoofer or whatever is sitting on the floor, and I don't care what it's made out of, it excites it and it causes vibration. On the little video that I do in there, I use just a little music box mechanism. Now that has tiny tines. They're moving plus or minus 0.1 millimeter. It's hardly any energy, not even like from a mid-range driver energy, more like a tweeter. So it's like nothing, but the tines do go down to 500 hertz. If I put that on a wall or a tabletop, it will amplify that music box by 27 dB with that tiny amount of energy. That wall or that tabletop is only moving a few billionths of a meter, but it's producing 27 dB with the tines movement from 500 hertz on up. Imagine what a driver, a regular monitor or subwoofer does. So when you have it resting on a floor, you're experiencing 4 arrival times, and you only want one. So the first one, the denser the material, the medium, the faster and the further sound energy travels through it. So when you're playing your speaker, the first thing that you experience is structure borne. The first arrival is structure borne via the floor to your chair, to your butt, via bone conduction to your ear. The second arrival is airborne from the loudspeaker to your ear. That's the one that we want, the only one that we want. The third is again airborne. These are reflections from the interior of surfaces. We can control those with acoustic products. And then the fourth one is structural again, and this is the big one. So when we, especially here in North America, with studs that are 2x4, we light fist pump will play 70 hertz. So whenever we play any music with 70 hertz, which is like any music you would play, it's going to resonate and it's going to act like a capacitor. So it's going to take that energy, store it for a moment, and release it later in time. And so you've got now loudspeakers playing after the original event has stopped. So time smearing, added resonances, and buzzes and rattles too. When those are controlled, I mean, most people have never experienced that. It hits all the sound quality attributes. You have more dynamic range, more articulation, spatial cues are more accurate, timbre is more accurate. It's anyway. So there you go. There's my speech on EVP. Okay, so now diffusion. So there's lots of reasons to add diffusers, and you know what? I wish that we would call them scatterers instead of diffusers. I think of diffusers as when something goes through something, like when you think of fluid dynamics or light diffusers, those things go through. And with diffusers, we're impinging sound energy on, and then it's reflecting and it's scattering. It's not going through it. So it would be, I think, better to more accurate to call them scatterers. But there's many reasons why we would want to add them. I don't know that we could have, once we have reverberation under control, and then adds scatterers, I'm not sure that we could have too much. I haven't experienced that. But once you get first order reflections and the reverberation times under control, especially in small environments like many of our mixing suites, you want to increase the sound stage and or the air, the space. You can do that with diffusers. In fact, you can really play with them to give it a sense of a larger space without distracting the accuracy. So some of the purposes are to, let's say there's too much absorption in there. We still got first order reflections that need to be addressed. You can put scatterers, reduce colorations, improve spaciousness, control flutter echoes, enhance the surround sound environment. Again, like for surround sound speakers, this can be very beneficial to make them sound more enveloping rather than, obvious. So there's a number of types of diffusers, and with any acoustical treatment, and I'm just talking about, interior topographical type of treatment, then it's going to be a matter of choosing the right type and putting it in the right location in the right quantity. So that applies to absorption as well as diffusers or scatterers. There's a lot of different types of diffusers. Number theory, you guys are probably familiar with that. And this is, so there's all these different types of number theory diffusers. And then there's geometric and volumetric. Excuse me, what I want to address are the number theory diffusers. This is where I find so much trouble. They seem to be kind of trendy right now, and people are, do it yourself all the time. Well, one, if it's not designed right, and it's the tolerance is like there is no tolerance. It's got to be designed right, and then it's got to be made right. If it's not made right, it doesn't work. To give you an example, this whole thing started with Manfred Schroeder. And when he was looking at butterfly wings and the spectral breaking up of colors, and he then applied this to acoustics, and he had his worker take some aluminum and make it corrugated with a number sequence that he had. Well, so then his worker made that, and they tested it and found, gosh, it was just behaving pretty much like a specular reflection, not doing what he thought it would do theoretically. Well, he discovered then that the worker hadn't made it properly. There was one error in it. If you have just one error in it, then it ruins it, and it behaves specularly. So there's so many poorly designed. I've designed so many of these diffusers for kinetics and so forth. If they're not done right, then they just don't work well. But then also the placement. Am I talking about? Okay. Yeah, before I get there, placement. No, I do have a slide for this. Okay, so we'll get there. So size matters. Take a look at this. This is a reflection. The top one is just the wall alone. So we're talking about we're doing 100. Gosh, it slipped off for some reason. The frequencies here. We're talking about 100 hertz here, I believe, and then we're adding a 1 foot pyramid type diffuser to it. And you see on the second down, it doesn't see that. The wavelength is so large that that it's unaffected by the diffuser that's there. Then we go to 1,000 hertz, and that same diffuser works well. And then we go to, say, 10,000 hertz, and now it works specularly again. So it needs to be understood that just like absorbers, they're not universal. They don't hit. They're designed for particular ranges of frequency, and I don't think that people get that at all. You see these, especially Skyline diffusers that they're made out of blocks, and now these things are really labor intensive, and they end up being really heavy, and they have maybe a 2-inch square face to them. Well, okay, so let's say that they are designed properly, and they are constructed properly. The best they're going to do is go down to maybe about 7,000 hertz. And so they're really limited as far as range. The top key on a piano is 4,000 hertz. And there's not many musical instruments that have fundamentals above that. So this isn't anywhere near getting into the foundation of music. I'm not saying it's not effective, but it has very limited effectiveness. Now, on top of that, you'll see this limited bandwidth diffuser being located in the wrong location. So imagine, let's see, here we go. Here's one that I'm talking about. Imagine that this is on a sidewall, and our sound source is to the left. You see it's a light source actually, but let's say it's a speaker, and I've got these diffusers on the ceiling or on, up above me or to the side of me. Well, look how the high frequencies are pretty directional, so it works very much like, it's ray acoustics, so it works very much like light. They end up casting a shadow on themselves. Sound doesn't impinge into those wells and then reflect and come back out. It's blocked. So a diffuser of this type is only effective if you've got it in front of you or behind you, where sound can impinge on it. In fact, I'm going to say most likely or most obviously, it's going to be most effective behind you because the sound source is then hitting it. Most of the energy is then hitting it and then scattering it. So that's a big one. They're geometric diffusers. Polycylindrical diffusers are really hard to beat. You can go much lower in frequency. In fact, we make one that's a 2 foot by 2 foot polycylindrical. It's flexible for one, so you can change it. And you don't have to worry about lobing with having a bunch the same. It is effective 150 degrees, so you can put it anywhere, and it's effective from about 630 hertz on up. So, and it's really inexpensive. It's super lightweight and beats the heck out of a diffuser like this. So I don't know. I mean, maybe these people think, oh, they're so cool looking. I don't know, but they are not being implemented properly and super limited as far as their performance and their application.
Norman, we have a couple of questions if you'd like to answer in between, or should we leave it for Q&A? Okay. All right, so there's one by Gary, but before, I'm sorry, Gary, but before asking his question, I have one question of my own because I know I'll forget it. So I'll just ask that first. As you mentioned, polycylindrical diffusers, and I've seen yours, they're pretty lightweight and just a membrane on the front. So I don't personally have a lot of experience with poly diffusers, but what do you think about the resonance of the air cavity inside? Can a polycylindrical diffuser be paired up as a bass trap as well, or maybe as a resonance trap?
Well, I don't know that I'd call it a bass trap because these are not very deep. Now we can make them that, yes, absolutely. The ones that we happen to offer on just standard every day is not deep enough. They're only 3.5 inches deep. So it's not. It can be used as absorption, but not in low frequencies at all because it's not enough depth. But that isn't to say that you can make something custom and do that. Yes, absolutely you can.
Yeah, I'm just kind of trying to develop a hybridized polycylindrical in a two-way format, like a bigger polycylindrical and a smaller polycylindrical paired together side by side with a concave surface in between that could act as a resonance trap. So I'm still modeling that and thinking about it. I should text you privately for that. Moving on.
Yeah, resonance, definitely. That's something you want to be considering. The other thing is with the polycylindrical, really the only open area is on the top and the bottom. I suppose you could put holes, you could make perforations and make
we're planning it top to bottom. We're planning it floor to ceiling trap, like a full. I'll talk to you privately about it.
Okay.
Moving to Gary's question. So that's a very interesting one. Gary asked, how does one determine where to place diffusers, assuming reverberation time and first order reflections are already under control? Plus, this question is specifically for small rooms measuring about 22 feet by 14 feet.
Okay, so
if you think that's going to be covered later in the webinar, we can leave it for now.
No, this is easy. So the first thing we would want to do is what are the reverberation times in the room? And then secondly, are the first order reflection points controlled? So then the existing reverberation times are going to dictate how we're going to address, excuse me, those first order reflections. We can put absorbers there. And again, we're mainly looking at trying to get, mid-range and high frequencies removed from those spots. We can do that with typical absorbers, or we can do that with polycylindrical, not what we just discussed. And they would be way too big. They would have to be they would take a lot of real estate. And so you say it's a small room. Well, a skyline type diffuser or number theory type diffuser, it's got to be effective down to say 500 hertz anyway, right? That's a lot of real estate. And so it's probably not going to work. But a polycylindrical or some other geometric type diffuser would work great there. So again, we've got a choice depending on the reverberation times of the existing condition. In the existing conditions, do we want to absorb it, or if there's enough reverberation absorption in the room, then we can scatter it and get rid of that first order reflection point. Does that answer it?
Not exactly, Norm. It's Gary. Okay. Can you hear me?
I can hear you.
Okay, yeah, I said, assuming that the reverberation time's under control, first order reflections are under control, then how does one determine where to place diffusers? Is there a general rule of thumb?
Yeah. Okay. Gary, there's never a general rule of thumb.
I knew that.
So, I mean, it completely depends on the speaker. How is it propagating sound into the room? What type of speaker is it? So that's the first thing that we would want to look at is, okay, so how are we going to place this so that it is most effective with the dispersion pattern that the speaker is giving us? And then after that, like I alluded to earlier, and I might be wrong about this, but I haven't experienced having too much after the reverberation times are under control and the first order reflection points, of course, are taken care of. Can you introduce too many diffusers? I mean, of course, you could end up covering up absorption that you need, but beyond that, I don't know that you could. It's not going to be, again, as long as you got the reverberation times under control. I don't know, but yeah, in answer to your question, of course, sound will tend to congregate in tri-corners. So a good place to put diffusers is in the corners up above, in front, and behind. That'd be a good place to put them. After we have addressed how maybe some speakers have a tweeter in the back, or the way they're a figure eight or whatever, we would then want to put a diffuser behind them, directly behind them. But yeah, first order reflection points, maybe they're not all taken care of. For every speaker, there's 6 first order reflection points that we have to play with. And maybe we can't, it's not desirable to use absorption in all of those situations. So again, that's where diffusers can help out. Hopefully that answers it.
Thank you.
I'd also like to add to it, that was a really great way, I think, to approach a control room in general. Other than that, also, what do you think about designing a control room in a way that diffusers work in as a feedback device in a certain time domain? Rather, I mean, if we already have the reverberation controlled, I think, Gary, if you already have the reverberation and first order reflections controlled with just absorption only, you're going somehow with the non-environmental route. Is that correct?
Say that again. Once I have them under control, I'm going with what?
I'm assuming you're going with kind of a non-environmental design route. Is that correct?
I'm talking about Norm's diffusers, using that.
Okay, so basically, in case you're not aware, like non-environmental is a Tom Hiddley's approach of designing control rooms, like in a way where the entire room is kind of controlled with the absorption only, right? So kind of I personally like to do it that way, and I would like to receive your input on it, Norman. If we use diffusers in a way that they are placed and designed for certain bandwidth, feeding reflections after a certain time frame, kind of like LED. Like LED uses the Haas effect to envelop the listening position, but more in a subtle way that the reflection is not really a kind of measurable on the ETC,
right?
But like in an amorphous reflection. What do you think about it?
Well, actually, that brings up a really good point in that, again, the number theory type of diffusers versus the geometric or in particular the polycylindrical. So you're not going to have phase anomalies with a polycylindrical that you will have with a number theory type of, and that's, there's so many reasons why number theory diffusers can be, they can introduce some colorations for a number of reasons. It's you have to be really careful with the polycylindricals or other geometric devices. You really don't. You can build larger diffusers for the space that enhance that. In fact, we also make a polycylindrical in a mobile stand. Now, this is something that audiophiles can enjoy. Not necessarily is it. Now, if you've got a small environment, again, this could be a benefit. You can have the diffuser placed at the first order reflection point. Let's say we've got a speaker right here, and the listening position, the mix position's right here. We can have a diffuser at that first order reflection point. We can maybe play with this distance-wise and spread the soundstage width. We can also, just like toe in with a speaker, we can play with that soundstage and timbre, right? So we can turn it on its axis as well. You could have a diffuser on the inside and give it more depth of space than you would have otherwise. So yeah, in small environments, diffusers can be very beneficial. You know, it can make your constraint kind of, that constraint kind of disappear. And then your work will be more transferable to other studios.
Makes sense, yeah.
Okay, convergence. Okay, again, with number theory diffusers, there is, you can totally relate, I'm sure, to having a tweeter mid-range woofer. There is going to be a convergence point, and the manufacturer, the designer, probably knows what that distance is. Where you can imagine if you are too close to the speaker, too near field to it, the frequencies don't converge evenly. Well, number theory diffusers, it's the same thing. And again, if it's a quality diffuser, that information is going to be available to you. And for mids and highs or something, it might be 1-3 feet. You've got to be away from the diffuser. If you're inside of it, then it doesn't do its work. It's not a scatterer. Again, with a polycylindrical type of diffuser, that is not the case. There's no distance difference. So convergence, distance, that matters. Design and construction, I already talked about this, how just a single error and all is lost. Here's a polycylindrical, and here is that test that I was talking about earlier with the ARC and the 19 microphones. This is the plot that you get, and so you can see that this the way it's positioned now, it's going to give you a horizontal scattering, and in the balloon plot there, it's showing you how well it's doing that, and as far as dB, white meaning like 100% is reflected. So that's the kind of test for scattering that you want to be looking for. Are you still there? Is everybody still there? Hello?
I'm here.
Okay.
Actually, I just got a call. I'm really sorry. I've just disappeared for a while. I just got a call. I'll be back soon.
No problem. All right, I will continue. So clarity, I thought, well, let's show some real world environments before and after. So here's this is at a small room before, and this is a good quality room to begin with. We just enhanced it with introducing some of our Polyflex diffusers. So the yellow bars represent the before, and then the orange are after we introduced 8 Polyflex diffusers. So this is clarity. This is about the time of early reflections that are, what we're trying to get here is an evenness and if you will, raise the bars. So this is a particular test standard regarding clarity, C50. Here's an example. I thought I had a whole bunch more tests, and maybe I do, and the slides just got mixed up. Here's our Polyflex mobiles, and in a couple of different scenarios. Obviously not studios, these are audiophile homes. Do I want to go into this? I think I pretty much already did. Yeah, I already covered all this. But over on the right hand side, I don't know that I covered all of this. So no high frequency limit. This is regarding our Polyflex. effective even at 90 degrees off axis, no theoretical listening distance, remains phase coherent. So yeah, it's you know, it's simple. All right, there we go. Open for questions. Uh-oh, he's on a call.
Hi, Norman. So, we got one question from, yeah. So, we got one question from Ed when you were talking about the diffusion confusion. And he asked that on the wall cavity resonance, do we tune that by increasing spacing of studs or by layers of sheetrocks?
Okay, so the question is about um, resonances of walls with sheathing, correct? Okay, and that could be on the floor, that could be on the ceiling as well as not, you know, not only the walls. So by adding layers of sheathing, you're going to reduce the movement, of course, because you're adding mass. But there's quite a lot that can be done.
I was also trying
just,
to ask about you said before when you made the comment earlier, you were saying a typical North American standard, if you will, are 16-inch or 24-inch studded walls. So how does changing the spacing of the studs tune the wall versus changing the thickness or number of layers or alternating thicknesses of layers of sheetrock if you're trying to build that wall right to begin with?
right. Okay, great question. So it's about depth. So you're the 16 versus 24-inch centers. It's not that. It's and that does address another thing, but you're still going to have that about 70 hertz resonance. If you add some sheathing to it, you're going to damp that resonance some because you're adding mass. I would suggest a couple of things. One, disconnect the sheathing from the studs so that they can't be excited by that resonance to the same degree. They won't be working together to excite. You're going to fill that. You're going to loosely fill that that cavity as well. That will also help damp. And in between sheathing layers, constrained layer damping compound would be beneficial. So again, instead of it going boom, it goes thud. Yeah, you can. To do a resilient layer over the studs is a huge benefit over from a resonant point of view, and also from a sound transmission point of view. You could have many layers and still not achieve good sound transmission transmission loss in the low frequencies, and you're spending a ton of money. It's a ton of not only material and labor, it's a ton of weight, and it's a lot of real estate. So you know, typically in any of the jobs that I do, we're talking 2 or 3 layers and of sheathing and dissimilar layers as well, so that the sheathing then doesn't, they're not all resonating at the same spot, and introducing constrained layer damping and not mounting it to the studs and filling the void loosely with fiberglass or rock wool or something like that. So it depends on a couple of things. Yes, sound quality. We talked about that. That's easier. The bigger one, and what may call out how many layers and the construction materials and methods, is going to be sound transmission. Sound energy is always a two-way street. If it can get in, it can get out. So in a recording studio environment or mixed studio environment, you don't want the drums entering and playing into your playback area. Or in a high-end home theater, you don't want your subwoofers getting into the structure and causing somebody who's trying to, you know, the kids can't sleep now. or you can't study or whatever. So hope that
So,
answers your question.
yeah, we have Asif asking, membrane absorption, should they be tuned to the first, second, and third mode harmonic or just the axial modes?
The question is about harmonics. How is it? I'm not sure I understood.
When you're developing a membrane absorber, how should you tune it? Like to the first, second, or third mode or harmonic, or just to the axial modes only?
Oh, I see. Oh, okay. Okay. Well, so the first thing that you want to do is you want to try and remove the harmonic in the audible range. So how do you do that? You can damp it. You can add some mass. You can constrain it. The way it's fastened. You might change the depth of I don't know what it is, but anyway, there's a number of ways that you can address that, but you want to make sure that the fundamental, I'd say the first, second, and third, any of those harmonics or resonances are not in the audible range. Sometimes that's impossible to do, so you want to just attenuate it to whatever your constraint is. But ideally, you're going to tune it so that the resonant frequency is at least an octave below the lowest frequency of interest, whatever that may be. So that's really kind of the goal is, remember when we're talking low frequencies, it's extremely difficult. These are really long wavelengths that have a lot of energy. And so they're really difficult to address. So depending on what the situation is, the resonant might be way up high where it's pretty easy to control. So yeah, there are different damping or constrained layer damping or means of fastening that can attenuate that.
So in conclusion, your answer would be to target all the excited modes rather than just the axial modes.
Well, yeah. So you would want to find out where are they and what frequencies are they at and how much energy are they at those particular frequencies, and what's the goal? Where do they need to be? So all that has to be determined first, and then you can begin to computer model, finite element of whatever the construction means is to eliminate that. So yeah, that's a multifaceted, really big question, but basically it is, if it's in the audible range, you want to try and control it at least an octave below your lowest frequency of interest.
Cool. I hope that answers your question, Asif. In case you have something more to ask, feel free to unmute yourself. Or does that solve the question? Give us a thumbs up, please. Address the modes only below the shoulder frequency. Of course, I think
yeah, I mean, for the most part, yeah, that's all you're doing. And in these small environments that we're talking about, and we're talking about playback environments, right? Mainly, this conversation is about critical listening, not performance venues. So we're talking in these critical listening environments. These are small rooms, and so they have not many modes, and they have modes that are therefore, because there aren't many of them, very perceptual. And so we want to, and depending on the size of the room, there's going to be a spot where there's enough of the modes that they are then not drawing attention to themselves. And that might be 250 hertz, 300 hertz or so. So let's say, in these small rooms that we are talking about, certainly 250 hertz and down is where we have room modes that we want to focus on. And we are wanting to address the, all we can really, the first, second, and third are going to be the most problematic with the most energy. There's so many ways that we can address room modes, and so let's discuss it, shall we? Okay. So the first thing is going to be the dimensions. The dimensions of the room are going to call out the room modes. And so then we'll know, okay, these are the room modes that we're dealing with, and this is where they live. And we can model that and get an idea, but then the real world might be a little different. So we really also need to investigate with instrumentation and perception. But anyway, dimensions, that's going to be the first thing. Then instruction materials and methods. So you can construct the room in that it's a low frequency absorber, and there's many ways to do that. Then there is placement of the listener, and the mix position. That's so important, and the speakers, so that we don't exasperate the existing room modes. And then there's interior, but we're very limited as far as low frequency extension. We can talk about diaphragmatic absorbers and adding those where they are problematic. So again, the right material type in the right location at the right quantities. And then we can, have I hit them all? We can EQ, or DSP or something to remove the peaks and get them under control. So that's the quick number of ways that we can address room modes.
Before we move further, am I audible? Can you hear me, Norman?
Yes.
Yeah, so before we move further, actually, I just got a notification from Teams that we only have 5 minutes left in the meeting because we scheduled it for 90 minutes. So I'm not really sure if this is going to end, but just in case it does, although it should not because it should last for a few hours. But in case it does, so I'm pasting a Google Meet link because there is some trouble with Teams today. So I request you guys to save the link just in case this meeting abruptly ends, join that link.
Okay, so that'll be emailed?
Not exactly, because I don't have the access to the database. It's all automated by Teams only. So I've just pasted the link in the chat here. If you can access the chat, you can just copy the link and save it.
Got it.
Just in case.
Okay. All right. Any other questions?
Yeah, Mihail asks, have you ever tested step diffusers and how they work? Like Cox's step diffuser, I'm assuming you are referring to Trevor Cox. How good those scatter and diffuse?
Well, they, though I really, so I was part of that committee back in like 2000 and, worked with Peter and for, this was an AES subcommittee on diffusion and how to test diffusers. And so anyway, that is evolving. I mean, acoustics is always evolving. We're always learning more, and we have been stuck with some standards that are older than me, and they really need to be updated. And understand that so many of these standards were designed for voice, so they are limited. Most of these standards, whether we're talking transmission or absorption or diffusion. Maybe not so much diffusion. They're only 125 hertz to like 4,000 hertz. And when we're talking about home theaters and music and so forth, we're interested in lower frequencies too. So anyway, there is so much that needs to be updated, and it seems that it's so difficult to do. But regarding diffusion, my favorite by far is the way it's done in NWAA labs. To get that balloon plot, it just tells you everything, and it's real. That's the other thing, is it's not modeled. It's not the scattering coefficient thing. It's not a small scale model. It's the real product in a real world application, and so I have 100% confidence in the results. So yeah, that means of testing for scattering should be implemented around the world. But yeah, it's not it's not cheap. It requires a large space and 19 expensive calibrated microphones and all of that. So anyway, but there is one place, NWAA in the state of Washington.
Perfect. I hope you got your answer, Mihal. In case you haven't, please let us know and you can unmute yourself to ask. Moving on, we have Christopher asking, hi Norman, for reverberation treatment solely for speech frequencies, what are the norms that you usually follow?
So the question is about for controlling reverberation for speech.
Speech.
Is that correct? Okay. So again, most of the speech out there, there's a test that I use all the time is called STI. It's a sound transmission index, or speech intelligibility index, and that's available to anybody. I think you can probably even get some free apps on that. But anyway, again, it's mainly just dealing with 125 to 4K. But the speech intelligibility is a nice way of confirming that this venue now has been properly treated and will be. It'll show you again via like third octave centers how articulate the speech intelligibility is at these different frequencies, and then it'll do an overall rating too. But it's a great, easy test tool, and you don't have to even do any modeling. You could really, since you're not talking about low frequencies, really, you can easily just, okay, we need to add some more absorption until we have a rating of excellent. That's what you're shooting for.
I have a follow-up question against that. Also, Christopher, if you think your question is not answered, or if you have a follow-up question, feel free to type or raise your hand. Meanwhile, let me ask my question. This reminds me, by the way, do you do any isolation chills for critical listening environments or any music facilities where the playback range is 20 Hz to 20 kHz?
You're asking if I do any isolation for critical listening
do you design any isolation chills for such facilities?
Yeah. Are you talking about floating floor systems and stuff? Isolation.
Anything. Yeah, soundproofing for studios. So okay. I've got a question. A lot of times, like when people are DIYing this, they use STC as a measurement for soundproofing. What do you have to say about it? I personally think that transmission loss should be measured all the time instead of following STC numbers on the web, like build this wall and you'll get this kind of STC. What do you think? I personally haven't found them to be very correct.
So STC is another one of those numbers where we can't go by a single number classification. We have to know what is the curve, across the frequency range that we're interested in. Otherwise, we have no story. I could have two completely different plots. I mean, curves that go, like this, and they could both say STC 55. Well, they're completely different, and yet they have the same number, So, all these single numbers attached to reverberation time, noise reduction coefficients, sound transmission, all those things are for the birds. I mean, they just don't mean a thing. So, I don't know if I answered your question, but you have to see the whole curve, the whole plot, to know what you're dealing with.
Yeah, I think you would suggest that we should measure transmission loss across all the frequency bands instead of following an STC number on the web, right?
Right. Correct.
I've been so much frustrated by these questions, and whenever I try to explain this to somebody, it sounds like I'm gatekeeping information while everybody on the web says different. So I needed you to say this.
Well, and the product that or the system or whatever it is that you're dealing with, that should have been tested by an accredited lab, and the report is available to you so that you can know how it performs. Otherwise, I'll tell you, as any acoustical engineer will, if you don't have that information, you can't use that product because you have no idea how to apply it. You don't know how it performs, So yeah, it would have, all of our acoustical products are, there's a standard test by an accredited lab, and we publish that so that for one, it's proof of performance, right? It's not just my verbal claim, but like this product here, the equipment vibration protectors, you guys have no idea the confusion of coupling versus decoupling in the audiophile world. It is a disaster. And so, and I seem to, my company is the only one that I know of that publishes the results. Nobody else is. So it's just like, oh, this sounds good. I mean, that means nothing to me. This does perform. We know exactly how it performs. And as long as you load it properly, this is the curve that you're going to get every single time. It is predictable, it's repeatable, it's consistent, and most importantly, it's neutral. You have no resonances in the audible range. You go with some kind of a coupler and you've got all kinds of resonances in the audible range. Change the material or the shape or the size or the load or the resting platform, that curve's going to change again. All those peaks are audible. They color the sound. You don't want any of them in the audible range. You want neutrality. And again, this is why I think it's important in recording studios, mixing studios, to isolate the source of vibration from the structure. Makes a huge difference. Quiets the structure. You don't have all that noise, buzzes, rattles, resonances interfering. It hits all the sound quality attributes. Makes your mix translate better to the next.
Yeah, absolutely. And yeah, that part is really true, that Norman's company is the only company who publishes the results. And I've never seen anyone else doing it. Even we don't do it. I mean, we are very insecure about posting results. That's one thing. But yeah, the way Norman publishes every result, testing data, that really shows how transparent they are. So you should definitely check that out. The website is called avroomservice.com, I guess. That's right?
Yeah. Yeah.
Yeah, definitely check that out, guys. Like the results and the testing data is like very intensively shared in great detail. Yeah. So moving forward, we have James asking, the AB rooms home were no doubt very useful in determining performance. To what extent were you able to measure the impact of environmental control systems, that includes heating, cooling, ventilation, etc., on performance? And how do these impact room design?
So, most of that stuff regarding, for example, ambient noise floor, and the HVAC contribution to that. I'm not sure if I can answer this question right or not, but for the most part, those goals are known. We know, for the most part, these basic things, we know how humans perceive them, or let's say the just noticeable difference, or the level of that is required to notice. So the noise floor, and that has everything to do with the dynamic range. If our typical residential noise floor is about 40 dBA, and so let's say we've got 100 dB max. The orchestra is playing triple forte, and so we've got we've got 60 dB of dynamic range. And if we lower that noise floor down to say 20, an NC 20, we just picked up 20 dB of dynamic range. Now, what's that mean? It means now we will hear low-level details that we couldn't hear before, and we will experience dynamic range that is not limited and not masking. Well, the same thing goes for reverberation times. We have a target that we know we want to look for. It's not anechoic, because again, that's not comfortable or natural. Room mode distribution. I look at room modes from 5 different human perception points of view. That I've got kind of a pass, no pass kind of a thing in these 5 areas. What else? So most of these goals we know, but then it's a matter of the acoustician to understand the existing conditions, the goal, and what the limits are. And often it's, like I say, it might be space, or it might be budget. but we have to make compromises, and we have to explain to the client the pros and cons of these different solutions. No room's perfect. They're all compromises. We just want to make it the best it can be. We want to optimize it to the best it can be under the known constraints. So we got to know the existing conditions, the constraints, and the goal, because those constraints might limit the goal. And as long as we all know that, then nobody's going to be upset when, if we don't establish that ahead of time, then we can open up a can of worms, because gosh darn it, it doesn't perform like you said it would, so yeah.
Hopefully that answers your question, James. And moving on, do you believe bass traps have a benefit in a small room listening room? In a small, sorry, let me repeat that. Do you believe bass traps have a benefit in a small listening room? Gary has asked this question, and I believe he has left the room already. But if you'd like to answer that question.
Sure. Well, it depends on what you're talking about as far as a bass trap. I think most people think of a bass trap differently than I do. For one, and I should mention it earlier, we don't, as an acoustical engineer, we never use the word soundproofing, and we don't like to use the word bass trap. It's an absorber, and to absorb low frequencies takes a lot of real estate. Yes, there's diaphragmatic absorbers that don't. There's Helmholtz resonators that don't, but that's a really high Q. That's going to be for a specific mode, and anyway, bass absorbers is going to be about controlling low frequencies, room modes in particular, right? So 250 hertz and down, and so those are large, long wavelengths, large energy, difficult. So again, as we discussed, construction materials and methods is a great way to address low frequency. So if we can build the shell so that it can flex, it will work as a low frequency absorber. It still needs to be sealed, airtight or watertight, whatever you want to call it, but the seals are resilient, so it allows it to flex. The structure is not hard fastened to one another. They're all, the floor is floating, the walls are independent of each other, the ceiling is suspended, and yet there's no penetration that isn't sealed resiliently. So you can have soffits, you can have risers that can act as low frequency absorbers too. That's something that is commonly done. So here you've got a large area, because again, large wavelengths, lots of energy. You need a lot of real estate to make a low frequency absorber. HVAC duct soffitting or risers, plenum kind of situations can be incorporated to be such. So that's often an opportunity that's missed, and should be and can be applied.
Yeah, great. As we see, a lot of people are leaving already. So do you
They're
guys
going
think
to bed, right?
Yeah, it's late. I think it's late. So do you guys think you can turn on the camera so we can just capture a memory for a moment? Like, if you're in in an environment where you can turn on your cameras, we'd love to see you all just for a photograph.
What do you want?
If we all can, a lot of people don't have the cameras
okay.
open. Yeah, I'm just capturing a photograph.
Okay.
Yeah.
Okay.
Shall I wait for the rest? Yeah, we have more people tuning in. All right, say cheese, guys.
Oh, this is nice. It's so nice to see faces.
Oh, yeah, isn't it?
Yeah,
say cheese,
it is.
guys. One more. There we go. Thank you so much, guys. Thank you so much. Do we have any more questions? I don't see any more questions, so I'll wait if
Okay.
somebody has any questions, and I'll ask mine if you have the time for it. So I
Sure.
basically noted down a couple of questions alongside the presentation. So the first of mine is related to your the products that you manufacture as the decouplers for speakers. I personally nowadays like to use only soffit mounted speakers. We don't do many freestanding rooms nowadays. But for both of the cases, would you like to explain how these products work in specific to the speaker model, or are these made for general purpose?
So it's all about load. When you're talking about mechanical
Mhm.
isolation and decoupling, it's a matter of compression, right?
Compression.
Deflection. And so, like with this material here, it's going to deflect depending on the load. Well, if we don't deflect it enough, or if we compress it too much, it doesn't perform as it's supposed to. So we make this is layers of fiberglass. We put in different amounts of layers, and we make different sizes and densities of layers of fiberglass to handle different loads. So, for example, we can make 3 of these hold a grand piano, which is 900 pounds, just by adding more layers, and it'll still perform exactly as this one does here. You mentioned mounting in a soffit, but you can still decouple it. So it could be mounted in a soffit resting on a shelf on these guys, and not touching anything now, suspended essentially. So yeah, otherwise it just gets, once vibration gets into the structure, it's not coming out. It's not coming out until it gets to the end of the building and goes outside. So yeah, it's
So these
important
are made for
and
load
actually,
specific devices.
yeah, it's
Sorry.
it's important and it's easy. The other we talked about suspending floors and or rather suspending floors, suspending ceilings and all that.
Ceiling.
That's expensive. That's out of the realm of most people. Well, shoot, this is going to do most of that work for a fraction of the money.
How much do these cost if you'd like to share, if you're comfortable sharing it on here?
Say that again.
How much do these cost if you're comfortable sharing that over
Okay,
here?
okay.
And
Let's see,
trust me,
these,
guys, it's not marketing or anything.
Right,
This is me being
right.
curious.
So we make standard sizes, large and small, and we make custom ones all the time. But the standard ones, the small, we make round and square.
Mhm.
These are US. They're 139 a piece, and you would need at least 3 to make a tripod, maybe 4. And then the large ones, again, we make square and round. These are 119 a piece, I think, and 239 a piece. There is a calculator on our website. So you go to products and you go to EVP and you scroll down and there's a calculator. So you find out how much does my speaker or equipment weigh, and it'll tell you what your options are. Now, for example, 4 of these will handle 304 pounds. So it'll handle most stuff. But if there's something that it won't, you can add another one maybe, or if you need to reach out to me to make some custom EVPs, we can do that.
Sounds good. Sounds good. So basically, we have set the point that these devices are just like the isolators that any other decoupler basically that has to be used in terms of load and deflection factors, right?
Yeah.
So,
Mechanical isolation is all about load. Yeah,
mhm.
and the resonant frequency.
So are these good for freestanding speakers as well?
Oh yeah.
Like for the near
absolutely.
field speakers, like 20
Oh,
kg,
yeah,
under
yeah,
20 kg,
yeah,
15
yeah.
kg. Yeah. And and what is the thing going on with rocking modes here? Do they handle rocking modes well too?
You're asking, do they rock?
No, the
What did you
rocking
ask?
modes in the way speakers transmit rocking modes via the stand, until and unless the speaker and the entire assembly is stabilized. That's what I've learned basically. That's what I've noted from my experience. That unless we are able to stabilize the entire assembly, there are some rocking modes, the modes that constantly go up and down within the speaker cavity, which are further transmitted to this
Okay.
stands.
Yeah. Okay. So there's a lot that we can talk about in this on that topic, but to answer your question, really, it basically is if you mechanically isolate, you're essentially floating, you're suspending.
Yeah.
That can rock. However, that's only going to be. I always tell my customers, expect it. If you push on it, if you bump it, if the dog or a toddler or something, if you're concerned about, then we need a larger footprint for more stability. Otherwise, it has nothing to do with sound quality or sound transmission. And this is what I want to state. That cabinet, whatever the speaker cabinet is going to move. It's going to vibrate. Whether or not I've got a decoupler or a coupler, it's going to move the same. This will have no effect on the cabinet moving. It will still move just the same.
So basically it doesn't do as, I mean, like just like any other isolator would, there's no way to figure out a way to stabilize a speaker until we soffit mount it.
Nor
Right?
is it's not important either. The only time it's
Of course.
Yeah, I mean, that movement of the cabinet is like I say, it's going to happen. And so, companies spend a lot on trying to make their cabinets rigid, with the material, bracing, fastening, all of that is, why some speakers are so darn expensive. But this will, whether you couple or decouple, will not affect that at all. Won't matter. So it's just then a matter of, is it safe? Is it going to topple if somebody, runs, bumps it or something like that? So again, you might have to go with, let's say this is the speaker and this is the stand. Maybe it can't be, you put the corner of the speaker over here. Maybe you have to make the footprint wider and put the corner of the cabinet so it bisects. That way we've got a wider footprint and is therefore more stable. Does that answer your question?
Yeah, of course, it does. Before we move, actually, we have more questions incoming. I was reading those as well. So, Sujal, do you think I've missed any questions? Actually, Sujal has been sending me the questions all along the session. So, I hope I'm not missing any.
No, you are not missing any question. We got like 2 new questions right now. If you can read those. Yeah, so Asif is saying that can we use these EVPs all around the speaker and then soffit mount it?
I'm not sure if I understand the question. You would need at least 3 under a loudspeaker. And that you would just set up as a tripod. We send a little bubble level with the first order. So, because we don't know where the center of gravity is. You don't know where the center of gravity is. You can move these around, 3 of them, until you've got the speaker level, because that's very important. 4 will give you more stability. The other thing that, and it's on the website, is that if you're talking about not a small monitor, but a full range speaker or a subwoofer, you really need a larger EVP, because you're talking about low frequency energy and you need more material to do more work, just like absorption, because that's essentially what we're doing. We're just converting mechanical energy into thermal energy. The fibers are intermingled, and so the mechanical movement causes friction, and that turns the mechanical into thermal energy.
Norman, let me clarify his question a bit. His question is more related to, like, when we are soffit mounting a speakers, we have to fix it stably from all 4 sides, from all 3 axes. So can we use these EVPs on the base and on the top and on the sides as well?
I see. Okay. Yeah, that's going to take
I hope that's what you meant, Asif, right?
It's going to take some engineering on. I'm going to have to help out with that. We know what the gravity load is, but what we have to also discover is, and we'll need some much less dense material to fasten it against a surface. So yes, the answer is yes, we can do that. We just need to know what the application is, so that we come up with the right density to perform properly.
All right, sounds good. Asif, you have your hand raised. Do you want to ask something? You may unmute yourself if you have any questions. I'll just lower your hand then. So we have RSC asking, could you elaborate on the coupling and decoupling distinction? And while you answer this, I just gotta go to give my dad some meds. Meanwhile,
Okay.
Sujal will be there to moderate the session. Just excuse me for turning my camera off for a bit.
Sure. Yeah, I can. So coupling versus decoupling. If we are going to couple, then we're going to be using some kind of rigid material. Now, again, you guys probably are not confused by this, but in the audiophile world, most of them are totally confused by this, and they will use spikes as feet. So they will actually couple the speaker to the resting platform, whatever that is, the console bridge or the floor or a shelf or whatever it is. So now they're communicating the vibration into the structure. They're directly conducting, so therefore coupling the vibration into the structure. So now the structure is acting like a loudspeaker. On the website, the EVP landing page, if you scroll down, there's a nice video that shows, I talked earlier about the music box mechanism. This has so little energy, and yet if I couple it to tabletop or something, it makes the whole tabletop amplify by 27 dB, and that's just a tiny amount of energy. When we decouple, we are isolating, and so we are converting the mechanical energy into thermal energy here via the friction that goes on with the intermingled fiberglass, so that those vibrations are not transferred to the structure. And again, like we talked about with noise control, it's always a two-way street. So those couplers, when you transmit into the structure now is vibrating, and the coupler has resonances, and that's why they're so audible. And I think this is where the confusion is it amplifies frequencies, and people go, oh, it's louder, so it must be better, or it just sounds better to them because it's louder, and that's not accurate at all. But it's so it resonates and it reflects. So it's also now transmitting into the speaker cabinet and interfering. And the floor that is now also vibrating is also going to then reflect and return back into the cabinet. So it's not a good idea to decouple. Then the speaker will become one audio reviewer said a better version of itself. It's certainly going to be a truer, more accurate version of itself because it's not interfering with external what's the word I'm looking for? Noise, or interference.
Great.
It can also be put under sensitive electronics too. Just to mention it, tube electronics, they're sensitive to vibrations. Turntables, of course. Anything with a digital clock has got a quartz crystal that's sensitive to vibrations. Tubes are microphonic, on and on. But speakers, that's your source of vibration. That's huge, really huge. People don't realize how big of an impact it is until you try this, and it'll take you about 3 seconds. That's the standard. It takes you about 3 seconds to go, oh my gosh.
Yeah, I get it. Sunil, do you think there are any questions that I overlooked in between?
No, we don't have any questions in between also, and I think we don't have any new questions also.
Any last questions?
I think someone is typing.
Okay, let's wait for them.
For a moment.
Meanwhile,
but I
have a last
answers your question, RSC.
Did we know? Okay, actually, I was just outside. I thought Norman was answering RSC's question only. Were you right?
Yeah.
Uh-huh.
Okay, so we got a new question.
No.
Okay, sorry.
It's Lou saying thanks, Norman, for this presentation. Thanks for joining in, Lou. It
Thank
was great
you.
with me. I have one last thing to ask from you. Like, it's kind of more like to understand your personal philosophy. How do you approach a control room design philosophy? Like, one specific thing in there would be how much do you think a control room has similarities to an anechoic chamber? Because that is kind of a general perception of a control room, that it's quasi anechoic, more like anechoic. And before you answer that question, I also want to ask you that in your design, in your company, do you design control rooms based on a specific format, a philosophy that has to deal with the existing architectural acoustics of the room, or it has to be a ground up room, or do you focus more on optimizing the existing architecture?
Oh, great questions. And again, I'm going to say that every job's unique, and so there's not really a cookie cutter formula, other than to say that again, we know what the goals are, we know what the targets are for sound quality. I'm also going to say that before we can talk about sound quality, we have to address noise control. You don't have sound quality if you have noise. So that's the first thing that has to be addressed. And then it's just a matter of, okay, again, what are our concerns? What are the existing conditions? And what are our goals? And what are our constraints? I have to have all that information before I can then make recommendations. I'm not an architect. I'm not. Don't ask me about decor, any of that. I can offer solutions from a decor point of view for others to decide upon. But yeah, I don't get into the decor at all. But you are, or I, as an engineer, every job is unique. You have challenges and that's what makes it fun. If it were the same thing over and over again, I wouldn't be doing this. I am constantly learning, and that's why I like it. It's different every day. It's a challenge, and I'm constantly learning. So yeah.
Great answer. Great answer. I think you have answered all the questions and much more my questions. Thank you so much for your time, Norman, and thank you all for joining in. Anything in the last that you'd like to say, Norman?
Um, well, I guess I should probably promote myself and just say this, that it used to be years ago, I had to come on site and I'm just going to throw this out there. I used to have to come on site with a couple of toolboxes and run some tests. Now I still do this. I go all over the world to do that, but it's no longer a requirement. There is now, and has been available for a few years, an app that works really well called Studio 6 Digital. And I'm not trying to promote it other than this makes it available to somebody across the world to make an impulse response of their room and send me the wave file. And with that, I can dissect it. I can look at combinations of time, energy, and frequency and know the characteristics of his room. It's not the same as me coming out there. If I came out there, I would have observations, subjective listening available to make further recommendations and run more extensive tests and investigate. But this will get me 75, 80% of the information of me going out there without me going out there. So it costs a whole lot less. It opens the doors to people for opportunity to address their studio environment that didn't exist before. Again, without the data, the existing data, you can't guess. This is science, and for the most part, there's a lot of things that we can test, that we can measure that are meaningless, and then there's also a lot of things that we can hear that we can't yet test. it is evolving. Like, for example, this software that's available now that wasn't before, and we can apply science rather than guess. And most people are guessing, and your chances of hitting the target while guessing are next to none. And with testing, we have also proof of performance. And recording studios, it would be great if they had that available to their clients. Here's proof of performance. Here's the reverberation curve of our room. Here's the noise floor of our room. Things like that would be proof of performance and could be a sales tool for people to use.
That's a really great way to approach it, and I just can't stress it enough how much people can actually save on consultations and the fee of a designer. Just like the way Norman mentioned, by if you can measure your room yourself. Most of the time, people are asking me to come over and measure their room, and without realizing how much it could cost and how much they could save by just the simple steps of learning. So yeah, I highly recommend if you are somebody who's planning to hire any designer for your room, consider purchasing some equipment that involves like just an omnidirectional mic. Basic ones do the job, but of course, if you can afford the expensive ones, they are always better. And just an audio interface with a laptop. REW Room EQ Wizard is just a free software. You can just learn how to use it in a few minutes, really, just in a few minutes. So
yeah,
think into
analyzing is another topic though, and that a lot of people I think get confused about, especially with Rue. That software has a lot of potential, but in the wrong hands, I'm seeing people constantly making measurements that are the wrong measurement. And not only that, they're making the measurement wrong. And not only that, they are interpreting the measurement wrong. And so in the wrong hands, it doesn't do you any good. But now we have the option of you record the impulse response test and send it to a consultant who can analyze it properly and make appropriate recommendations.
Yeah. Absolutely. That is something that has to come as a caution with Room EQ Visit. I have to talk to them as the developer of this company, that if you learn how to use the software, you should not just think that you have learned acoustics as well. If you want to know how these measurements translate or how to read these measurements, you have to spend in the time, you have to spend in the effort that every acoustician goes through. So it's rather better to just measure the room, listen to your acoustician and let them analyze it if you can't spend the time. Of course, I don't say that do not DIY. You should DIY, but if you want to DIY, you have to learn it and spend the time. And
best to take it to an expert, like anything,
of
right?
Course. Absolutely.
Yeah.
On that note, I think it's time that we can wrap up. Before going, I should also mention once again that Sujal. Thank you so much for coordinating this session. Otherwise, I would have left so many questions. He kept popping me up with all these responses that I missed. And again, I must stress, he's a great mixing engineer, guys. He has mixed a lot of my records that in the time that I used to produce music. Now I don't get the time for it, but if I had, I would go to him all the time. I've mentioned his Instagram in the chat. Go follow him, check his music out. He's just amazing. And also, I'll just put a link to our WhatsApp group that I moderate, and it's a fairly inactive group, I would say. But yeah, once in a while we have a good discussion. So if you guys want to join the WhatsApp group to discuss room acoustics, you can find the link in the chat. And also, I'll just put in Norman's website link as well. Check those products out. Just so I spell it correctly, avroomservice.com. Is that correct?
That is correct. Yep.
For some reason, I haven't got the link though.
I want to mention, if anybody is interested in these, we have right now, if you use a code called a code MHO, it stands for Mr. Holland's Opus. You'll get 10% off, and in addition, we'll apply 10% to Mr. Holland's Opus Foundation, and that is a foundation that provides instruments into the hands of kids that are less privileged. So anyway, we're promoting that charity by doing that.
So the code is once again MHO. That's all, right? I'll just
MHO
mention
for
it in the chat.
Mr. Holland's
Keep-
Opus.
I'll just mention it in the chat as well.
Perfect.
All right. Thank you so much, Norman, once again for
All
spending
right.
the time. Thank you all for
Thank you.
joining in. Have a lovely
Thank you.
evening and a lovely day in the US.
Right, right.
See
Yeah,
you
it's
all.
still, no, it's noon now. It's no longer morning. So yeah.
Have-
Well, thank you so much.